All right, according to LeetCode, this problem has medium difficulty. Let's get into it. We're dealing with the kth smallest number in M sorted list. So what does it look like? Let's look at this diagram. I think it can make it plain. So we have these lists and they're all sorted in ascending order from lowest to highest. And we are given a number k. So we want to find the fifth smallest, is it smallest? Fifth largest, smallest element. The fifth smallest number in this entire group of numbers. And we get 6. That's our task. How are we going to do it? So in this case, we get to 50 where, okay, we don't have up to 50 elements in this. So the greatest among them is the kth smallest element. Okay. Then for the third, you just get the third one. And you can see how, let's say 50, and there were actually 50 elements. This would be something you would really want a computer to do for you. So that's all there is to that. Let us move to the solution. How do we solve this problem? Well. Okay, so for example, this list, we want to get the sixth smallest element. So k is 6 here in this list. What are we going to do? We're going to push the first element of each list into a minimum heap. Okay, so 2, 3, and 5 are going to go in there. Next, we're going to remove the top element and add the second element of the first list into the minimum heap, because this came from the top elements came from this first list. So when we take something out of there, we move whatever it came from, wherever original list it belonged to, we push the following value onto the heap. So 6 is going to go in there. As you can see here, 3 becomes the smallest thing. And then we keep doing that until we get to number 6. 6 goes in. If we take 5 out, 5 came from this list, so 8 is supposed to go on there, as you can see. And we keep going until we get to k equals 6. Boom, and we get our value. That's it. Now what does this look like in code? We have it here, and so we're passing a list that is the group of numbers and the k value that we want. What we want to do is loop through. In fact, I'm gonna just simplify this code a bit. That here. I can get rid of this. All right. Okay. So we have the heap that we're going to use to keep track of what's the smallest thing. The first thing we do, we loop through everything in here, and if there's nothing in any particular group, in any particular list, we skip that particular iteration. Otherwise, we put the first element. What is this? Okay, we put the first element of each list in the heap. Okay, so that's the main reason we're looping like this, is so that we can place, what is this? So we place the first element of each list in the minimum heap, which is what we did here, for example. And once we're done with that, we get to work. So while there's still something in the heap, we pop the first thing. So the first thing would be the current smallest number, where it exists, what list it belonged to, the position of the list it belonged to, and so for instance, when we pop this, we would get smallest number here would be 2. List index, this is the first list we're evaluating, so it would be 0. And then the position of that number of 2 in that index is 0. So we would get 2, 0, 0, for example. Then we increment the numbers checked. And if we get to k numbers checked, we break out of the loop because we're pretty much done. Otherwise, we say, okay, we increment the number index again because you took 2 out, so you need to put 6 inside the heap. That's what we're doing here. So we increment it, we check to make sure that there's something to add, to take from here and put in here. Make sure that, let's say 2 wasn't the last value, for example. We push that same list index, but this time an increment 1 position later, the list index and its index into the minimum heap. And we go on and on and on until we empty the minimum heap. And once we're done, we return the smallest number, the last smallest number we found. That's all there is to this problem. Thank you so much. Oh, before I forget, lest I forget, big O notation. So we have this Stirling approximation again, which has been popping up every time we've been dealing with this, with heaps and priority queues lately. And it evaluates to m log m. So m log m, n log n, pretty much the same thing. Like m plus k log m is practically a constant factor here, kind of. So m log m is a good approximation, honestly. And then the space complexity is O of m because of the total elements in the heap, the number of total elements that get added to the heap. So yeah, in the worst case, you would end up adding every single thing to the heap. So there's that. That's all. An educative a day can keep unemployment away. A video about it might make you a hit. Yeah, I had to say it. Bye-bye.